Hello everyone, my name is Shabani Mchomvu and today we are going to discuss some questions on numerical methods. This is a topic that is in pure mathematics, advanced level, and now we are going for solving sessions. So we'll see some questions on different papers, starting with the year 2024, question number 7, usually it's a numerical method question. And the question has got three parts, as you can see. Part A, we are required to state two limitations of the Newton-Raphson formula. We are required to use, in part B, the Newton-Raphson formula to show that the kth root of a positive number A is given by this equation, that x sub n plus 1 equals to k minus 1 over k bracket x sub n plus c a over k minus 1 brackets times x sub n raised to 1 minus k bracket. And the last part, C, we are required to use the trapezoidal rule. This belongs to numerical integration with 5 ordinates. Here we are provided with the ordinates, but sometimes some questions comes with the number of strips, but here we are provided with the ordinates. Now to approximate the value of the integral, here you can see the function inside the integral sign, 1 plus x cubic bracket raised to a half. Or we can say the square root of 1 plus x cubic. Now this is integration with respect to x. And now the answer after approximating, the approximate value should be corrected to 3 decimal places. So starting with the concept of Newton-Raphson in case A, the Newton-Raphson formula, another formula. This is given by xn plus 1 equals to xn. Here we minus f of x n, then over f of f prime of xc sub n. So that's the Newton-Raphson formula. So we are required to state two limitations of the Newton-Raphson formula. The Newton-Raphson formula, normally it exists if some conditions are observed. Number one, the function that we are dealing with, it has to be differentiable. So we can say here the limitations now of Newton-Raphson formula, that number one, the function has to be differentiable. It means we choose the function that can be differentiated. If differentiation cannot work on that function, on that particular function, this method cannot work. So number one, the limitation we have to observe is the requirement of the differentiable function. Differentiable function. But number two, this differentiated function, it is not supposed to be equals to 0. So that's also the condition. It is not supposed to be equals to 0. For this formula to work, we want this differentiable function f prime of x of n should not be equals to 0. Because when it is 0, some operation and manipulation can never be done. So that's very important. Also, we can add the other limitation like the concept of initial guess. A solver has to be very, very careful when choosing the initial value to start with. Normally, they are choosing 0, but 0 is not the best number sometimes. In most cases, 0 is not the best number to start with. So sensitivity on the initial guess of the value that we are starting with is very important. Also can be a limitation for the formula to work properly. So we say the concept of sensitivity to initial guess. sensitivity to the initial guess. So the number that we are guessing for the first time, it has to be the best number where approximation around the true value or the true root can work. If we do not make best initial guess, it means now the formula, when we use it, it will result into convergence or divergence far away or from the true root that we are looking for. So sensitivity to initial guess is very important, but the most important thing that the derivative should not be equals to 0. So you choose the function that's where derivative can never be 0. And the requirement of differentiable function. So for this continuous function that we're dealing with, we have to be very careful when we are dealing with the function which are differentiable. If are not differentiable, the formula cannot work. So these are among the limitations. Now, part B, now we are going to apply now. We are told use the Newton-Raphson formula to show the kth roots of a positive number R is given by this equation. So in case B, so we are provided with the information that the kth root, so we can say, we can let now, letting x raised to k now equals to a. And remember, a is a positive number. A, we know, is a positive number, but a is greater than 0. So here, normally in numerical method, we are dealing with the root of a differentiable function where f of x will be equals to 0, where we obtain now the approximate value of that function. So here, it means we make some environment to have x raised to k minus a, it means equals to 0. So that 0, now we can replace it by say f of x now equals to x raised to k. Now from there, we can say now, from the Newton-Raphson formula, that x sub n plus 1 equals to x sub n minus f of sub n over f prime of x sub n, this way. So from the function there, then maybe we can develop, we can say f x sub n equals to this one, equals to x sub n raised to k minus the constant number, the positive number r. Now on finding its first derivative, x sub n prime, now we apply the power rule of differentiation here, so will be k xn then k minus 1, because this one now a becomes 0. The derivative of a is 0. So from there now we plug everything into the formula. So this now becomes x sub n plus 1 equals to x sub n. Now we minus, here we have this one, minus a bracket, then over k, then xn, now k minus 1. So from there now, it's a matter of simplification until we make the face to look like this expression here. So from here, maybe we can start by taking minus, this one will be x sub n, here is k, over k xn, then k minus 1. Now we minus, we plus, that's a, over k now, xn, and k minus 1. So it has to be like that. So we have tried to separate. Yes. After now separating these, so here maybe we can factor out or simplify more and saying xn, x of n, here will be like, because here we have the common terms here, this x of nk and this x of nk minus 1. If we simplify, we end up getting, this will be k minus k, k minus k minus 1. So it will be like k, then k minus 1. So it becomes k minus k plus 1. So it means now we'll have x sub n raised to 1, then now over k, this way. So it can be like that way. And then now we plus that a. So this now we can make it, we can find the reciprocal, then it'll be 1 minus k, then here over k. So we end up at that stage. So if that to be the case, sorry, then now again, so here we have possibility now we can see 1 minus k, and here a over k is just there around. But now here we can factor out x sub n. So if we factor out x sub n, we are going to make 1 minus, it will be 1 over k. Yes? Then now we plus, so here will be a xn now 1 minus k, then here over k. So something like that. Now to make this environment here now, we need to manipulate here. So if you simplify here, it means k will be the LCM. So we'll have k minus 1. Now we plus a, then x1 minus k here over k. So from here now, we can decide now to take out or factoring out k minus 1 over k, because we want to make this face here. So it will be, if we factor out this one, it means now we remain with this divides here will be x sub n, now we plus. When this divides here, remember here we have a over k. Now we divide by k minus 1 over k. So it'll be a over k, we times, then here we reciprocate k minus 1 upside down. So this and this now will cancel out, and it now remains a over k minus 1, then in bracket, here we have x1 minus k, x sub n, and bracket, then in brackets. So from there now, we can check if we have approached. So x sub n, a over k minus 1, then this one. So this now we can say, now we have shown the expression x sub n plus 1 now equals to that one that was required. So now that represents the kth root now of a positive number a through the Newton-Raphson formula. So from there, in part C now, case C, we are required to use the trapezoidal rule. This is among the numerical integration method for approximating the root of a function. And now we are provided with the details, here we are given ordinates. N means the number of ordinates, that is 5 ordinates, and you are told to approximate. You are required to approximate, this from the interval 0, 1, then 1 plus x cubic, and then a half here dx. Correct it to 3 decimal places, but what is needed to use the trapezoidal rule. So solution, now from the numerical integration, trapezoidal rule, that's the integral from a to b, given the function y or f of x. Now with respect to x equals to h over 2, now bracket, here we have the value of the initial value of x here when we plug into the function of x. Now we get y naught. Now from this y naught now, or we say y1, now we plus 2 summations of middle ordinates. These middle ordinates. Now then we plus yn. It means the last one. That is produced by the last value of the limit. Then from here, that will be now the formula. The formula that will help us, that's the trapezoidal rule. So from the numerical point of view, from here we need to develop this value of h. So h now, the interval is given by, now we take the higher limit, we subtract the lower limit, that this we term as b here, b minus a over n minus 1, because we are provided with the ordinates. So we have to take n minus 1. If it was a concept of strips, it means we just put n strips. Normally, it's appear an even number. So here, b here from the integral value, the highest limit was 1. So 1 minus a, which was 0, over n, that is 5 minus 1. So now we get 1 over 4, which is the same as 0.25. So that's the interval between one ordinate and the other ordinate. Now from here, we can develop now the table of values, table of value for the function f of x equals to, now we take this integrand here. That is what we are taking now. The same as say the square root of 1 plus x cubic, of 1 plus x cubic. So from here, now we'll have the value of x, and here we'll have the value of y, or f of x. That is f of x. So now starting with the value of the lower limit, that is 0. Then now we just add the interval between one ordinate and the other. So 0 plus 0.25, it is 0.25. Then we proceed, we add 0.25 until we reach 1. So here becomes 0.5. And when we add 0.25 here, we get 0.75. And again, when we add 0.25, we get this and that's 0. Then 9, 0, now we end up getting 1. So now that will be the simple table of value that we are looking for. So as it means, this now will represent the y naught, and this now will represent the yn, and these betweens, these now will be the middle ordinates. So these are the middle ordinates from the table of value. That will be the middle ordinates. So what we do now, we can just take our non-programmable scientific calculator, and now inserting that equation, the function of x, that is the square root of 1, we plus x cubic. So here we calculate. So when it is 0, we know here it becomes 1. And when it is 0.25, so we have a number that is 1.00. And now we can see correct to 3 decimal places. So here we can have some number of decimal places above the 3. So maybe 82. When it is 0.5, it is less more to 1.06, 06, then 60, yes. Now 0.75, it is less more to 1.192, 4240, yes. And when it is 1 now, we get radical 2, which is 1.4142, yeah, 13, maybe 5, yeah. So we get something like that. So from there now, it's a matter now of plugging each and everything from the table value to the formula. So So here we go back. Now we say now from the trapezoidal rule. The trapezoidal rule. So integration of the root of 1 plus x cubic dx from 0 to 1 equals to h. Our h there is 0.25. Then we say over 2 brackets. Why not? From the table there it is 1. Now we plus 2. So we find summation. Now we sum all these middle ordinates here from the table of value. So we can clear data. So we take 1.007782. Now we plus 1.06 again, then 60 we plus, last one 1.19, 24, then 24. Yes, between 24, 24, yes. So this is less more to 3. So here we get 3.26, then 0.866. Now we plus y sub n, it is here 1 point. It is 1.41, then 42135. Yes. So from there now, we have this 0.25 when we divide by 2. Here we get 1 over 8 brackets. So now we find that's 1 with plus 2 brackets, 3.26, then 0.8, 0.82608, then 66 bracket 6088. Then now we plus 1.4142, then 135. So this now become 8.93, then 59, 455. Yes. So now from there, now we times with 1 over 8. So we get 1.11699 and so forth. But here we are told to correct it to 3 decimal places. So from 0 to 1, 1 plus x cubic with respect to x now is approximate to 1.1. 3 decimal place means it will be that way. So we approximate here, becomes 7. So that is correct to 3 decimal places. And up to that point, we are through with that question number 7, paper 1, advanced mathematics in the year 2024. Thank you very much.